Today we will be solving polynomial and rational inequalities. We're going to be using two methods today. The first method will be solved by graphing, and the second method will be solving algebraically. The first method, solving by graphing, is by looking at a graph and determining where the y values are either greater than or less than certain values, and then answering where our x values give us that. Sounds a little bit confusing. Let's look at an example. For instance, looking at this graph, we see the function is sometimes above the x-axis and sometimes below the x-axis, and sometimes it has some x-intercepts. Looking at our question, it asks us to solve for when my function is greater than 0 and when our function is equal to 0. I like to split that up into two separate thoughts, my greater than and equal to sign, because one of them means it's positive and one of them means it's equal to 0. We're first going to solve for when f of x is equal to 0. You can notice that I have three x-intercepts, and so at -3, at 1, and at 5 are my x-intercepts. Because it's asking me to find when my function is equal to 0, I am going to include my x-intercepts in my answer, because this is when it's equal to 0. And then we look at where the graph is positive. Being greater than 0 means positive. So looking at the graph, we can see that it's positive over here and over here, meaning in between the boundary points -3 and 1, and from 5 going all the way to positive infinity. Now notice that I've done two things. I've looked at the graph and highlighted where the y value is positive, but now I'm going to answer for the x values where that's true. So my interval will be the interval from -3 to 1. And my other interval will be from 5 to infinity, because those are my x values where this is true, and I'm going to join them with a union symbol. Making sure that you use the brackets when there's an equal to symbol, and that use parentheses for infinities. But notice that all the values that are in my final answer are x values. My question asks, when are my y values positive and when are my y values 0? My answer is, on these x values, that happens. Question number 1 asks us to do the same thing. We're solving this inequality by graphing, and we're given the actual function equation instead of just being given a graph. But we're going to have to identify those pieces. We should know from looking at this function that I should have an x-intercept at each of these two locations, and I should know about their multiplicities, so that one of them will cross through the graph and one of them will touch. Notice that my graph mirrors what I thought would happen at the -3. It touches and stays on the same side. At the +1, it crosses from the graph, up from the negative to the positive side. Let's go ahead and use this graph to separate our x-axis into regions. So you can see that I've drawn some lines at our x-intercepts at x equals -3 and x equals 1, and I've highlighted the areas to show you the three regions that I am dividing the space into. But I'm going to erase my highlighting so we can look at this graph in a cleaner environment. So here's our graph, and we want to ask ourselves, what is the question asking us to tell us? It asks us, when is my function greater than 0? And greater than 0 but not equal to 0. So we have the function is negative in this region. We know that it's 0 on the -3. We know that it's negative in this region, it's 0 at 1, and then it's positive in this region. We're asked to find the region where it's positive, so that would be this region and this region alone. And so we're going to answer by giving those x values. That would be from 1 to infinity, not including the 1, because at 1 the value is 0. And so there's my interval. all the numbers from 1 to infinity would, when I plug it into this function, give me a positive value. When we solve rational inequalities, the method is very similar to what we did with the polynomial inequalities. We just had to keep one thing in mind. We have not only our x-intercepts to be aware of, but also our asymptotes. Now our asymptotes are going to be holes in our domain, so that can never be part of our answer. For this question, we're asked when is my rational positive and 0 again. Now we can tell when it's positive, and we can tell when it's 0. We have to make sure not to include endpoints where there's no values. Let's see what I mean by that. I'm going to separate my regions. My asymptotes are already helping me separate this into regions, but I need one more region at the 0. And so we actually have 4 regions. So we're going to be looking at the values in each of these 4 regions to see if they satisfy what our question is asking. Recall that we get the regions by looking at the zeros of our numerator for our x-intercepts and the zeros of our denominator for our asymptotes. So looking at our first region, we can see that the values in that region are negative, and so we'll say that's negative. We know at our asymptote, our function is undefined. In the next region, it's positive, and then it's 0 at x equals negative 2, and then it's negative, and then again it's undefined, and then it's positive. That is, I want to get the regions that satisfy the positive and the 0, but I don't want to include any undefined regions or any negative regions. And so I'm going to take the 2 regions that are highlighted. And so we're going to say from negative 4 to negative 2. Once again, at negative 4, my function is undefined, so I'm going to use parentheses. At negative 2, my function is equal to 0, so I'm going to use a bracket. And then again, from 1 to infinity. At 1, my function was undefined. At infinity, we always use a parentheses. And so this is my solution set in interval notation. Question number 2 asks us to solve the inequality by using the graph of the function. Now the function equation that they gave us has one factor in the numerator, so that means we have one x-intercept, and we have 2 factors in the denominator, meaning that I have 2 vertical asymptotes. Because of this, I should know that there's going to be 3 lines separating my graph into 4 different regions. So here's our graph. I've highlighted the 4 regions so you can see them. It's sort of hard to see that R0, which is at our y-axis, our x-intercept over there, is also one of the lines that's dividing up one of our regions. I have the boundary points for those regions clearly defined down at the bottom. At x equals negative 2, the function is undefined. And then at x equals 0, my function is equal to 0. And again at x equals 1, my function is undefined. The question is asking, when is my rational less than 0, or when is it negative? That would be this region is negative, this region is negative. And so only these 2 regions are going to satisfy this inequality. Let's write our solution in interval notation. That would be going from negative infinity to negative 2. We don't ever include infinity. Our negative 2 is undefined, so we're not going to include it. And we're also going to union from 0 to 1. Now at 0, my function is 0, but the question is asking not when I'm equal to 0, but when I'm less than 0. So I'm not going to include my 0, and I'm also not going to include my 1 because it's also undefined there. And here is my solution set written in interval notation. So on the board, I have rules for solving inequalities algebraically. Now I want you to take a close look at steps 3 and 4. It says to use the boundary values from step 2 to break up your number line into regions. That should sound really familiar because that's the same steps that we did when we were solving something graphically. And we divided our x-axis into regions depending on where our x-intercepts and our vertical asymptotes were. And then step 4 is to determine if each region is negative or positive. Now we won't have a graph to reference, so we can't just look at it and see if it's above or below the x-axis. And this step's slightly different because we will have to be plugging in values into our function to determine if it's positive or negative in those regions. I also want to point out for step 2 that you do have to write the related equation if you're going to separate out any factors or make any statements. If we have a polynomial and we're saying that that polynomial is greater than 0, it would be not correct to say that each factor is greater than 0. I will not allow you to make those statements. You have to say the related equation has these factors, and those factors have these zeros, which I'm going to put on my number line. But you cannot put that each factor is greater than 0. The reason this is incorrect is because if I have two factors that multiply to be positive, it's not true that both of them have to be positive. If both of them are negative, they still multiply to make a positive. So I can't limit my answers just to where each factor is going to be positive. So you can't make those statements because they are not true. Instead, we write a related equation. We make our function equal to 0. Then each of those factors is equal to 0, which we know is true. And at those zeros, at -3 and at 4, the function is equal to 0, and then we'll decide if it's positive or negative in between my zeros. So this is the proper way to go about doing it. You absolutely have to make sure that you're writing an equation before you separate out each factor. So make sure that you do step 2 with equal signs. Question 3 asks us to solve the inequality algebraically. So according to step 1, we want to isolate our function on the left-hand side of this inequality. And that's already been done for us. So we can move along to step number 2, which says to write this as an equation before solving. So make sure that you write it as equal to 0, and then we're going to factor and find all of our x-intercepts. Once again, I can't stress enough how much this needs to say equals to 0 and not greater than 0, because as I split each factor away from the original, it would be incorrect to make that statement with inequalities. We're going to put each of our solutions on our number line, and we're going to let it divide it into 4 regions. 3 values divided into 4 regions. So you can see we have 4 regions, and at the top of our boundary points I put that at -3 and at 0 and at 1 we find the value that is 0. Now in between our zeros we have to discover if those numbers are going to be positive or negative. To do that, I like to pick numbers in between our values and plug them into the highlighted factored equation. It's easiest to plug it into the factored function to find out if the function is positive or negative in each region. Now you have to be very careful when picking your test points. It was easy to pick the -4, the -1, and the 2, but in between the 0 and the 1 there's no integers, so you might have to pick 0.5 or some other fraction to be able to plug it into your function. When I plug -4 into the function, I get x plus 3, and x minus 1. And the reality is that I don't really care what the number is. It's just when I multiply them out, I want to know if it's going to be positive or negative. And this region is going to be negative. My next region, I'm going to plug in -1. So I get x plus 3, and x minus 1. And when I multiply that out, I get positive 4. So this region is positive. When I plug in 0.5, I get x plus 3, and x minus 1. And like I said, I don't know what that number is, but if I multiply a positive times a negative, my answer is negative. And I'm not going to take the time to multiply that out, because all I need to know is if it's positive or negative. And then when I plug in 2, I get x plus 3, and x minus 1. And that becomes positive 10. Once again, I just care if it's positive or negative when I plug it in. And so above the number line, you can see I have my positive regions listed, my negative regions listed, and my zeros listed. And I want to know if they are positive, because the original question says, when is my function greater than 0? So I'm looking for my positive regions. I don't want to include zeros. So I want to include the two regions, but not their endpoints. Let me write this in interval notation. I'm going to go from negative 3 to 0, not including the negative 3, not including the 0. And then I'm also going to go from 1 to infinity, not including the 1, not including the infinity. If you take any number on either of these two intervals, you'll find that when you plug it into the original inequality, it will make it true. Therefore, all of those points within those two intervals are solutions. Question number 4 asks us to solve this rational inequality, but you should notice that it is greater than or equal to 1, not greater than or equal to 0. So we have to do a little bit of work on step 1 to isolate our function. Notice that the first thing I did was to subtract 1 from both sides, but in order to be able to combine all these terms, I need to make that 1 into a fraction. I converted the 1 into a 2x plus 4 over 2x plus 4, but remember that it was minus 1, so I need to make sure to subtract the entire numerator. By that, I mean distribute this negative to all the terms in that second numerator. So you can see it became minus 2x and minus 4. I just went one step further, and I like to take all of my coefficients out if possible, and have my leading coefficients as 1 whenever possible. So I factored out a negative out of my numerator, and I have negative times parentheses x plus 8. My denominator, I factored out a 2, and so I have 2 times parentheses x plus 2. I'm finally done with step 1, so I'm going to write this as an equation and take out each of my factors and make them equal to 0. So you can see that I took the numerator, set the numerator equal to 0, and that solved to find my real zeros, or my x-intercepts. And I took my denominator, set it equal to 0, and that is going to find my undefined regions, or where my vertical asymptotes are. When looking at my number line, at my real 0 of negative 8, I'm going to put the value of 0 over the number line. At x equals negative 2, I'm going to write undefined above that value. And then you can see that this has separated my number line into 3 regions. You can see those 3 regions, and all you have to do is pick a test point in each of those regions. I've chosen the values negative 10, negative 4, and 0. I'm going to plug each of those values into the highlighted equation below. So I'm going to get negative x plus 8 over 2 times x plus 2. Now, if you remember from last time, I actually don't care what the values are. I just care if it's positive or negative. I'm going to go ahead and figure it out. I get negative 1/8. And so that region is going to be negative. Plugging in negative 4, I get negative x plus 8 over 2 times x plus 2. And so that's going to cancel out to become positive 1. So that region is positive. And our last one says 0, so we're going to get negative x plus 8 over 2 times x plus 2. And so that gives me negative 2. So I'm going to say negative here. Now, I want to look back at my inequality when I'm comparing it to 0, not when I'm comparing it to 1. So we're going to look back at the inequality over here. I want to say that my rational function is greater than or equal to 0. That means, because I'm looking for the greater than or equal to 0 portions, I'm looking to see where the function is positive and when it's equal to 0. You can see that I have the positive region right in here, but that I'm equal to 0 on this endpoint, so I'm going to include it, and I'm undefined on this endpoint, so I'm not going to include that. Therefore, my answer should be negative 8 to negative 2, including the negative 8, not including the negative 2. And there is my solution set to this rational inequality. Make sure you practice this. I see a lot of mistakes in students' work, mostly on this part right here, where we're subtracting a fraction and we're forgetting to subtract all of the entire numerator. The other mistake I see is not setting our inequalities as equations and then forgetting to write it as equal to 0 and using the test points. So sometimes the students will just keep the inequality symbol and then get confused when you have two values that are greater than 0. And so make sure that you set it up the way we've done in class. I will be looking for each of these steps as you are solving this on the exam. Alright, so now you know what to practice. Go have fun, and we'll see you soon.